Hello, everybody. This is Mr. Fasoni. I'm starting up the video for Chapter 1.2. So as you recall, Chapter 1 is linear functions, and we're moving into Chapter 1.2, which is more about transformations of linear and absolute value functions. So we're going to be expanding a little bit on what we talked about in 1.1, have some review as well, and hopefully this will help you guys firm up your understanding of how these different transformations all work. So our goals are to write functions representing translations and reflections, write functions representing stretches and shrinks, and write functions representing combinations of transformations. So more than one of those three transformations at the same time. So our first concept is horizontal versus vertical translations. So recall from the previous section that translations are when the graph of a function is moved up or down, or left or right, or a combination of both. It could be up and left, up and right, down and left, or down and right. And this is done by adding or subtracting in the equation or in the function. So we've got two different possibilities. Our first one is when there's a vertical change. For some reason, my pen is misbehaving. One moment. The first one is when there's a vertical change. To get a vertical change on an equation, we're going to be adding or subtracting on the function itself. So by the function itself, what I mean is f of x is my function, whatever the function is. We're going to add or subtract some value to that function. So for instance, if I had, write it over here, if I had f of x equals 3 times the absolute value of x, let's make it more complex, minus 5 plus 6. Say that is my original function. Instead of it just being the parent function, I've already got a function where some transformations are happening. Well, if I want to translate vertically, I can add or subtract some other value to it. Say I wanted to take this function and shift it or translate it let's say 2 units down. Well, if I wanted to translate this original function here in red, f of x, if I wanted to translate it 2 units down, I could just take the function and subtract 2 from it. Well, if I subtract 2 from one side of the function, well, I can do that from the other side of the function as well. So I could rewrite this as 3 times x minus 5, the absolute value of that, plus 4. So I took this function, which already has 3 separate transformations happening, and I moved it down by 2 by subtracting 2 from the function as a whole. Remember, my original function is that guy there. 3 times x minus, or 3 times the absolute value of x minus 5 plus 6. I'm subtracting 2 from it. In fact, let's use a different color for the subtraction here. I'm subtracting 2 from it, so I subtract 2 from that side. 6 plus, or positive 6 minus 2 gives me positive 4. So that's my new function. I took the original function, I subtracted 2 from it to translate the whole graph of that function down by 2. So when we talk about vertical transformations, it's always in regard to some addition or subtraction of a value k. For horizontal translations, I want to translate horizontally to the left or to the right. I'm still adding or subtracting, but that addition and subtraction is actually happening to the input. On the previous one, it was the whole function meaning f of x. For the input, that means I'm affecting the x value before I continue doing the function. So I'll be adding or subtracting on the input. So let's say I have the same exact function as before. F of x equals 3 times the absolute value of x minus 5 plus 6. If I want to, with this one, if I want to translate it, let's say 2 units to the right, well, what I can do is I can subtract some h value from that. We use this way of writing it with a subtraction sign instead of an addition sign for the horizontal translations, because all the values work backwards. So if I have a positive value, it's actually going to take me to the left. So this is just a little way to help us remember that the horizontal values are always going to be backwards from what your intuition would tell you. So if I want to move it to the left by 2 units, I would add. And if I wanted to translate it to the right by 2 units, I would subtract. So if I'm translating this original function, 3 times the absolute value of x minus 5 plus 6, if I'm translating that whole function to the right, that means I'm going to be subtracting 2 from the input. So I could rewrite this function as 3 times x minus 5 minus 2 plus 6. So in this case, my input value is this guy right here, the x. What I'm going to be doing is modifying that input value by subtracting 2 from it. I'm already subtracting 5, so I'm going to subtract 2 more to get my new equation. And my new equation, or my new function, is going to be 3 times the absolute value of x minus 5, oh, not 5, the absolute value of x minus 7 plus 6. That becomes my new function with a translation 2 units to the right. So just remember, if it's horizontal, it's going to be on the input. And if it's vertical, it's going to be on the function as a whole. So first goal, writing translations of functions. We already did a couple above, but let's just do one more. We've got this function, f of x. What f of x does is it takes the input x, multiplies it by 2, and then adds 1. This is a linear function. So we want to write a function g. So our new function name is going to be g, and the graph is a translation 3 units down of the graph of f. So it's taking the graph of f, the original, or the original function f, this whole guy right here, and it's translating 3 units down from that graph to create g. So all I'm doing is f of x equals 2x plus 1. And to create g of x, all I'm doing is taking f of x and I'm subtracting 3. Well, in this case, it's going to be 2x plus 1. That's my original function, minus 3. I can rewrite that again. That's just going to be 2x minus 2. The minus 3, that's not what I meant to do. The minus 3 is my translation, 3 units down. And since it's a vertical translation, because it's down, since it's a vertical translation, we subtract 3 from the entire function as a whole. Let's try another one. Write a function h, whose graph is a translation 2 units to the left of the graph of f. And I forgot, let me finish this. F of x minus 3 is actually another way to write g. So this, after we do the translation, becomes g of x. So our new function is g of x, which is equal to 2x minus 2. I'm going to do the same thing here. I'm going to have function h translate 2 units to the left, so that's going to be horizontal. Okay, so now we're going to be affecting the input because it's a horizontal translation. So again, I'm going to write my function over here. My original function is f of x equals 2x plus 1. I need to alter my input this time. So my new way of writing this function, I can think about it as f of x. Well, I'm going to be translating 2 units to the left. If I'm translating 2 units to the left, well, that's a movement towards the negative direction on the x-axis. Well, the opposite of negative is going to be positive, because remember, everything's backwards when we think about the x-axis. So it's going to be 2x plus 2. I'm affecting my input by the value 2. So everywhere my input is, I'm going to have to modify it by the number 2. This is where it gets kind of crazy. It's going to be 2 times x plus 2, because this x is my input. I'm modifying my input. I'm turning it from x to x plus 2. So this x here needs to become an x plus 2 here. Adding 1. Do some quick multiplication. 2 times x is 2x. 2 times 2 is 4. Add 1. Finish it out by turning it into 2x plus 5. That becomes my new graph. And again, I can rewrite this as just the new function, h of x. So that's goal number 1. Next up, we'll talk about reflections. Same idea. Recall from the previous section that reflections are when the graph of a function is mirrored vertically. The x-axis acts as the mirror. What I mean by that, if I have some function, let's say it's pink. Let's say the graph of my function looks like this. It can be anything. If I multiply that function by a negative value, it's going to reflect itself. Over the x-axis. So it's a vertical reflection, and the x-axis is acting as the mirror. Every value that was above becomes below, and so on and so forth. So that's a vertical mirroring, but we also can mirror stuff horizontally. We'll talk more about this as the semester continues, or as this chapter continues. And in that case, the y-axis acts as the mirror. So I'll give a quick example of that as well. Same idea as before. But if I want to mirror something horizontally, let's say I've got a function that creates something that looks like, I don't know, like this. That's my function. And if I modify my input value, it will reflect it horizontally and create a function that looks like that. And again, the y-axis this time is acting as the mirror. Everything on one side gets mirrored to the other. Either way we reflect, we are multiplying either the function or the input itself by a negative value. As you can see right here, If it's affecting the whole function, my function in this case is f of x, I put a negative sign in front of it. If I'm making a horizontal reflection, I'm then affecting the input, which is right there, and I'm putting that negative sign in front of the input while it's still inside the function. So let's see this in action. So again, I've got a starting function. F of x equals the absolute value of x plus 3 plus 1. That's where I'm starting from. I want to create a function g whose graph is a reflection in the x-axis. So it's going to be a vertical reflection because the x-axis is acting as the mirror. So all I'm going to do for my function is I'm going to, sorry, I had a little hiccup there. I'm going to multiply the entire function by a -1. So let's try that. My function is f of x equals x plus 3 in absolute value plus 1. Well, this is my whole function currently. So the whole expression is my function. They are equivalent. If I'm going to reflect it vertically, that means I'm going to stick a negative sign out in front of my original function. So I get f of x with a negative sign in front. Well, I can do the same thing on the right side of the equation. I have to put a negative sign in front of the whole function, though. Well, the easy way to do that is to put the whole function in parentheses. Remember, a negative sign is effectively a -1 that's being multiplied here. So this negative sign is going to multiply this, and it's going to multiply that, both parts, the x plus 3 in absolute value and the +1. When I do that, I get my new function. Still negative f of x. But it's going to be equal to negative sign, absolute value of x plus 3. That's the only way we can write that. And then the negative sign times +1 becomes a -1. So we have to be careful there. That negative sign is changing every part of the function. So it's changing the first part of the expression, the absolute value, and the second part of the expression, the add or the +1. And now we've reflected across the vertical, or reflected vertically across the x-axis. So same thing again, let's do function h. Again, it's a reflection of the y-axis, so it's going to be a horizontal reflection of the graph f. This one's actually a little easier to write this time. Again, f of x is equal to the absolute value of x plus 3 plus 1. And what I'm doing this time is I'm doing a horizontal reflection. So what that's going to require is that I put a negative sign in front of my x. I modify my input first. Well, still have an absolute value. It's going to be x plus 3, and I've got +1. So the only thing I'm doing on this one is just sticking a negative sign right there. So basically, when I input some value x, in the normal equation, I just put in x and then add 3 to it, and then take the absolute value of whatever that is. In this situation, I put my x in there. The x goes into the absolute value, but then I turn it into a negative x. Then I add 3 to that, and then take whatever that number is and take the absolute value of that. So that becomes my new function, and then I can rewrite it just like I did with the previous one. Actually, I forgot to do it again. Let me fix this one more time. This should be h of x now because I've created a new function. And the previous one, I forgot a step, should be g of x. So remember, when we're doing these functions, it's easy to forget. We're changing the function from f of x, which is our original function. We're creating a new function. We're calling it g in the first case, h in the second. Be sure to name your functions. All right, so that's the end of goal one. Goal one had 2 parts. The next 2 are going to be fairly fast. Goal 2 is about horizontal and vertical stretches or shrinks. So again, recall from the previous section that stretches and shrinks are when the graph of a function looks stretched out or shrunk down. This is done by multiplying large values for stretches or small values for shrinks. So for a vertical stretch or shrink, again, we're multiplying the function. Function's always directly connected to the vertical. By a large number, and by large I mean greater than 1 to stretch, or a small number being between 0 and 1 to shrink. We're going to call that number a. Whatever we're multiplying by is going to be a, and we're multiplying that by the entire function. There's my stretch or shrink value. For horizontal, it's the same idea, except I've got an error that I need to fix. I'm going to make some edits. I typed things really quickly, but clearly didn't check my work. So for horizontal, remember, horizontal is backwards from how we think it's going to work. For a horizontal stretch or shrink, I can multiply the input by a large number, greater than 1, to not shrink it, or not stretch it, but in this case, to shrink it. So in this case, large numbers will cause a shrink, and small numbers will cause a stretch. It's backwards from how you feel it would normally work. But remember also, a horizontal stretch is the same as a vertical shrink. They're going to look the same when we graph. When I stretch something vertically, I shrink it horizontally. The sides come in. If I stretch something horizontally, I shrink it vertically. It looks like it's shorter because it's getting wider as I stretch it horizontally. So just remember, they are reversed from each other. And again, horizontal affects the input. So let's see what happens here. So I've got goal 2, writing stretches and shrinks of functions. So I'm going to take f of x, which in this case is the absolute value of x minus 3 minus 5. What I'm going to do there is I'm going to write a function of g, which is a horizontal shrink of the graph by a factor of 1/3. And I'm also going to write a function h, whose graph is a vertical stretch of the graph of f by a factor of 2. So the first one is actually the harder one of the two in this case, because I'm doing horizontal first. So f of x is x minus 3, absolute value, minus 5. If I want to do a horizontal shrink by a factor of 1/3, this is where things get a little bit crazy. So the factor is always going to be reversed. If I want to shrink the factor by 1/3, then I have to multiply it by the opposite of that. Because remember, small numbers actually cause a horizontal stretch. So how I do that is I take the reciprocal, only with horizontal stretches and shrinks. I'm going to take the reciprocal of this value, 1/3. So my factor is 1/3. The reciprocal then becomes 3/1. Remember, reciprocal is just a fraction that's been flipped. It's the multiplicative inverse, meaning if I took the reciprocal of a number and multiplied it by the original number, I would get the value 1. For instance, 1/3 times its reciprocal is 3/1. 1 times 3 is 3. 3 times 1 is 3. 3/3 is 1. So the reciprocal of 1/3 is 3/1, or 3. So if I want to do a horizontal shrink on this new function, I'm going to multiply the input by that reciprocal, which is 3. And I'm going to apply that 3 everywhere that the input shows up. There's only one spot the input shows up. And there's my new equation. So finally, I'm going to rename this guy the name that they want me to use, g. So g of x is equal to the absolute value of 3x minus 3 minus 5. And that's going to be a horizontal shrink by a factor of 1/3. Excuse me. So let's do function h. Same idea. Starting with f of x. I want to do a vertical stretch by a factor of 2. Well, that means I'm going to multiply the entire function. Let me move this. So f of x is equal to the absolute value of x minus 3 minus 5. I'm going to multiply the entire function by 2. So 2 times my original function is going to be equal to x minus 3 minus 5. Ooh, 2 times that. Let's rewrite that a little bit clearer. 2 times put it all in parentheses because I'm multiplying the whole thing. Absolute value of x minus 3 minus 5. Since that's a multiplication, I have to use my distributive property. So I get 2 times function f of x is equal to 2 times the absolute value of x minus 3. And then 2 times negative 5 is going to be minus 10. So finally, I can rewrite the whole thing. Let's clean it up. H of x, that's my new function, is equal to 2 times the absolute value of x minus 3 minus 10. And now I've done a vertical stretch by a factor of 2. All right, on to the last concept, combinations of transformations. So recall from the previous section that we can combine translations, reflections, and stretches and shrinks at the same time to create a new function. Note that the order of the transformations, let me rephrase that, the order that the transformations occur does matter. So we'll see that right here. So let the graph of g, so g is going to be our new graph. It's going to be a vertical shrink by a factor of 0.25, followed by a translation 3 units up of the graph f of x equals x. So this is my original function. Pretty simple function. But I'm doing 2 things to it. First off, I'm doing the vertical shrink. Then I'm following that by a translation 3 units up. That order is important. You're going to see the difference in just a second. So let's do it in the correct order first. vertical shrink by a factor of 0.25. Well, if I want to do, and actually I'm going to move over here for this. If I want to do a vertical shrink, again, that's multiply by the value. So if I'm doing a vertical shrink of 0.25, I'm multiplying the entire function by 0.25. So first, step one is going to result in 0.25 times f of x, which is going to equal 0.25 times x, or 0.25x. Step one is done. Now I have to translate the entire graph up by 3 units. Well, up by 3 is an addition by 3. So if I want to fix this up a little bit more and get the second transformation in, it's going to be 0.25x plus 3. And actually, I should write that a little bit more. A little bit more clearly. Up by 3 is an addition of 3. So right now my function is equal to 0.25 x. So if I want to modify it again, it's going to be plus 3 to both sides of the equation. Oh. So I get 0.25x, and I'm adding 3 to that. This becomes my completed function, 0.25x plus 3. Now I'm going to rename it to the name that they wanted me to use. G of x is equal to 0.25x plus 3. And we're done. But what happens if we do this in the wrong order? Let me do the addition by 3 first, then the vertical shrink. So this is the correct way on the left. Let's do the incorrect way on the right, in the wrong order from what they specified. Still starting with f of x equals x. But let's say I do the addition by 3 first, translating it up 3 units. Well, that would mean that I have f of x plus 3 equals x plus 3. So I'm doing the plus first, even though the order specified the other direction. So my new function becomes x plus 3. Then I want to do 0.25 times my x plus 3. So I'm going to multiply by 0.25. Let me rewrite this. I'm just going to call this a new f of x right now. If my f of x is x plus 3, and I'm multiplying it by 0.25, I get this. 0.25 times f of x, which is going to equal 0.25 times x plus 3. Because remember, f of x is my entire function. If I do the 0.25 second, I have to multiply it by the entire function as it is at that step. So I end up with a situation where I'm doing distributive property, using distribution. 0.25 times x becomes 0.25x, just like below. So far, so good. But 0.25 times 3 ends up being 0.25. 7.5. So we get a different equation. And this equation, or this function, is incorrect. So as I said in the slide, order matters. If you've got 3 transformations in a row, 1, 2, 3, you want to do them in the order that they are stated to go in. If you don't, you could very well end up with lots of different possibilities for the function that aren't what the function is describing. All right. And that is it for this video. It's a little bit shorter than the last one. I hope to keep these closer to 45 minutes. So enjoy your day. Please check out the homework and come with questions on Thursday or Friday. All right. See you guys soon.